Okay, for next 1 hour, we're gonna have a class for makeup class, but at least it's comfortable, right? So I think we're gonna really have 1 hour. That's what I'm gonna do until 7:30. That's what we'll do. Okay, we start to talk about probability functions and amplitude measure. That's what we're gonna cover this evening. And when X is ensemble, then you must define the ensemble using the probabilistic term, not the deterministic matter. You can't really determine what to do. So if this is a whole stochastic process, the core is the probability, okay? Or statistics is really same thing. So this chapter 2, I'm going to cover all the basics that you need to apply. And simple terms for probability functions or the engineering viewpoint. First, to try to get the implication first rather than the mathematical definition. What is it? What is the probability? Well, probability is simply the chance. So in engineering, the viewpoint, the probability is relative frequency of occurrence. What's the chance? For example, you have a die which has a 6 phase. What's the chance when you throw that it appears the 1? Some people call the event. The simple viewpoint is probability is relative frequency over the chance of that particular event that occurs, okay? Let's say experiment is repeated n times and the outcome A occurs. So this is just a notation that I'm using. NA means number of event A. It occurs. Very simple. Capital N, number of the event A occurs. So let's say number of event A is, let's say, small n. Small n is equal to n bracket A, close bracket, okay? Then probability of A, which means probability that event A appears or event A occurs, is defined as I use a PROB, which is a probability that event A occurs. Is a limit, n goes to infinity for better estimate. But again, we live in the finite world, so n is finite usually. So, but mathematical expression, this is correct. N approaches to infinity. Then n is a total number of event A, okay? So it could be 100 higher, 200 higher, 300, approaching to infinity for the exact sense, okay? What's the NA? Number of event A occurs, right? So you have dice. When you throw here, then what's when you throw it, what's the chance that the 1 dot appears, which is only 1/6, right? total event is 6, because when you throw 6 times, is a total is a 6. You can have a 10, 20, 30. Then event A, you designate the 1 appears. The event A could be the event that 2 dot appears, so on. So limit small n over n. This is a chance. So engineering point of the view, the probability that event A occurs is a chance. Same thing. So a little bit more kind of the math, the simple math. So probability now, probability distribution function. Then we're going to define the probability density function. That's easier. If you define the probability, the density function, then you have to get into integration. So here is a simple, to define the density function, you have to differentiate. So distribution function, let the measured value at time t1, A be, the A is an event. Event is situations that x at time t1 is less than or equal to the threshold value chi. I think this is called a chi, isn't it? Anybody remember? This is like, I used this for damping, or say zeta, I call the zeta, but that something like this. I think that's called a chi. You check it out. So chi is a threshold level, the limit. You set, well, here you can set at the particular point along here, giving the particular value for chi. Okay? And at T1, this is at time T1, all the way. This is one sample record, another there. Then that event A is the x value at time T1 is less than or equal to the chi value. Chi is deterministic value. Okay? So that's the event. Everybody got that, right? Then probability that event A occurs means the probability that x at time t1 is less than or equal to the given value chi. That's what you're looking for, probability. So this is n is a total number of the trial or experiment or event. You throw the die 100 times, then n is 100 times, okay? Then what's the chance number of the event that x at time t1 is less than or equal to the chi, okay? Chi is a fixed value. So here is a number of measurement or experiment with amplitude less than or equal to chi at time t1. So this is what the probability that event A occurs. Question. This is a definition, so you can't afford not to understand. Very straightforward. Event, okay? Probability that event A occurs. Event A is x at time t1 is less than or equal to the chi. Okay, then whenever use the subscript x or x1, this is a random variable, okay? So here is x, random variable x. This is all x sample record here. And same as in the previous page, but it gave here showing clearly the threshold level, the chi. It's a fixed value. So you're looking for, as you look at here, you're looking for the probability that x at given time at t1 is less than the chi, right? So in this case, only let's say 3 events here. And the x value is higher than chi. Over here is higher than chi. And here is less than chi. So what's the probability that event A occurs? A is the event x at time t1 is less than chi. What's the probability here? Charu. 1/3. That's it, right? This is a finite number of trier. So in this case, it's a 3. So number of trier, we did a 3 here, but that's a capital N, supposed to go higher, approaching to the infinity. So it's good to know as first engineering sense, okay? So less than, so in this case this is the chi, fixed value of the chi. Then you can read this as a capital P. Capital P is the probability distribution function. And small p is probability density function. Simply speaking, is dp over dx is what the probability density function is. So the maximum value of a probability distribution function is equal to 1. Why? Why not 2? What you're looking for is the probability, right? This is what you're looking for, probability. Then if it's a distribution function, less than equal to, this is all going and going, everything below the value of chi. Chi is along here. Then there's 100% chance to hit the chi value. Chi is like approaching to infinity, right? So probability is 1, is sure, right? But if you move to the other side here, chi is right here, is 0, doesn't mean anything on the below 0. So if chi is 0, everything is above 0. So chances are, if I set like this wording, x is less than or equal to 0, right? That's what you're looking for here, which is no chance, right? Nothing goes below 0. Nothing goes below or equal to 0. That's why its chances are really 0, but this is, you could have said as a non-zero value here, but should be usually at 0 is 0. Okay, so this is chi, the limit at time t1. you are looking for at the given time, because it's a dynamic time history values. That's what you're looking for. So x at time t1, and this is a sample function of the ensemble. You have to look at that way, right? So you have to get the definition straight, then it's easy. And this is, as you look at it here, but here is a wording, algorithm. What does it mean, algorithm? One sample record, statistical property of one sample record implies the whole ensemble of the sample group of sample record. So rather than dealing at time t1, when you're dealing with the algorithmic process or algorithmic data, then you can deal with the one time record, right? That's about all you need. Lots of class of the problems fall in this category. So I said, for the special case of stationary, that means here is algorithmic data, then probability distribution function will be the same at all time and can be determined from a single measurement or single experiment, the x. Just the one record is what you need. So now the probability distribution function of x, sometimes I use x here, usually put the small x here as a variable. And put the x right here to make sure you're dealing with x as a random, the variable. And is equal to the probability such that x is less than or equal to the chi. Okay? This is what that really means. So when you're dealing with just the sample record, which is algorithmic process, then I can deal with the limit t goes to infinity, approach to larger time in this case. As I mentioned this afternoon, if I say 100 seconds is too short, then 1,000 seconds. 10,000 seconds, for example, that much record. Too small, 365-day record. Vice versa, total time, which approach to large value, and this is a time such that the x, the random variable, is less than or equal to the chi value. Do you feel it? The meaning, you have to feel it for the meaning of it, okay? So here, this is, let's say total time that you're dealing with is from here to here. Total time is a t here. Then here, this is a time that x is less than or equal to chi. This is a chi value right here. If you just draw the line here, this amount of time plus that amount of the time plus that amount of the time is exactly right here at the numerator. You see that? Yeah. This is the time below the chi. So all this is above the chi. This is the below the chi. As I passing, it's all above the chi. Chi is right here. As I passing, this is the region for below the chi. this region above, this region below, but if you cut the total time t as this, capital T is the time from here to here that goes to the denominator. Chevam, it's clear, right? Clear. Gusto, clear? Yongbin, should be very clear. I'm not forcing you to say clear, but it is clear. Again, when you're dealing with the probability distribution function, so probability distribution function is a P. For the P, you are always dealing with this. So it could be a lambda, could be the threshold, okay? Then threshold is same as a chi, right? So here, then you have, like you can have xt, right? So one history, algebraic process, you can tell right away. But if I put x at time t1, then that's a questionable whether that's a stationary or not. If I put, some people could use I as a subscript, indicate clearly it's talking about the ensemble of the record. As a chi approaches to minus infinity, means it goes to negative infinity. Everything stops around here. If it keep going, then probability distribution is equal to 0, right? Make sense? Choru. I can tell by looking at your eyes, approving, disapproving. Clear. If the chi is approaching to plus infinity, then distribution function here is surely 1. Everything is included, right? Approaching negative infinity, not including. Everything is away, right? Negative infinity. So probability P is between 0 and 1, between 0 and 1. That's the maximum range. And now the probability density function of random process, stochastic process, ensemble at time t1, probability density of random variable x at time t1. Time t1, that implication is stationary, not the algebraic process. And the density function is dp over the dx, not the dt. This is x is random variable here. X could be a function of time t for engineering problem. So it's a dx, okay? So this is another view of PDF. You know, be careful. PDF has a couple different implications in this course. PDF is a probability density function, right? Some people blindly could use that as a probability distribution function, PDF. But whenever you hear about the PDF, I'm talking about the probability, the density functions. Okay? Probability density function. And this is showing another view, okay, for the algebraic process. Algebraic process, you don't have to deal with the random process at time t1, because one sample record represents the whole ensemble of the process. So here the probability x, this notation is belong to. This notation is used as belong to. Or you can say within. Either way is all same meaning. And the time duration is a t here. Time duration t, that x is within or belong to the delta x chi. So here in this time history, this is a delta x chi is at the middle. So delta x, put the chi as a subscript, which you can say that there's a delta x chi is like this interval. So this is what does it mean here for this whole thing in the numerator? This is a duration of the time that x belong to between this. So which means that hatched time duration, summation of hatched time duration, this plus that plus that plus that. Okay? Setting the t, well, the denominator is the whole duration. Duration could be from here to over up to here. Or could be longer. Or could be longer. Okay? But at the same time, well, this is what direct the ratio total time to delta x chi durations. The delta x chi, the finite, the x amplitude. And here, this is using the duration or time, or this is a probability that x belong to or within delta x chi. And another expression using the amplitude, the probability density function, I can say delta x approaches to the zero. In other words, delta x chi here approaches to zero. So it's like, if you look at carefully, the density function is differentiation of the distribution function, which is really slope if you look at it, right? Well, velocity is dx over dt. It's a slope for the curve in engineering sense. So delta x approaches to zero. So this is really the definition. Is probability, I use a PROB, now it's reduced down to PR, it's the same thing. The probability that x belong to or the within delta x chi over the delta x. Okay? I demand you really follow me on this. It's no differences. So the P times, if this is a limit approaching it, then this approach to dx, right? So you move this guy to here as a px dx is equal to the whole thing. And this 2 looks like it's very clear, but later this is coming back. So you have to capture here correctly. P dx is a probability that x within the dx chi. Okay. Now this is a property of probability function, but what's the whole area under? Just the common sense, engineering sense. What's the area of a whole probability density function? This is a probability density function, small px. Okay, this is random variable x. So if you integrate the whole area under the probability density function, then what's the area? What's the total area? Is equal to 1. Okay, so here, if I say this could be something like in this class the height of a student, you know, how tall you are, height. Then this is from for example, Chongwan, what's your height? 170, no, 185? Huh? 178. I thought you were 185. No? I thought I am about 170. You are much taller. 178. Okay. And Chusong, what's your height? 73. 73, same. How about Gusto? 165. Let's say 165 could be here. And maybe 180 could be here. And this is like a typical normal distributions, right? So does it make sense? As you look at the density function, as it goes higher and higher, the curve comes down, right? What does it mean x2 here? Probability such that x2, x is x2, which is 180 centimeters, right? What does it mean? So in this class, for example, if you get the total area up to the x2, right? Up to the x2, then you got the, for example, 0.80. What does it mean? 80% of the height in this class belong to up to about 180 centimeters, vice versa. So if you take that area here, that's what exactly this is. This could be 180, this could be 160. So area is a probability such that in this case is between. The value here is between 180 to 160, is whatever the value you compute here. Okay, so now the left, this is a probability such that up to the x2, which is area from minus infinity to x2, this is a probability distribution functions up to x2 here. So this is, let's say, 180 centimeters. So when you take the area up to the x2, then what's the probability up to the 180 centimeter is what the area of the probability density function. But this is a normal density function, so height or such a thing is pretty normal. This is symmetric about the middle. But like gust wind speed, okay, gust wind speed distribution function is no longer nice normal distribution function. It's not. So it's not like this, but rather the gust wind usually it has a skew. You know, if you look at the mean could fall right here, but for the normal distribution, mean falls right at the middle. So this is called a gust wind. Also, such a distribution is called extremal distribution. It has a skew into it. Okay, so hurricane, same thing. Typhoon, typical typhoon is the same thing. Probability from negative infinity to positive infinity, what does it mean? Everything is included. Then chances are always occurs 1. Okay, so now let's start to look at some special function. Special function, sine function is quite well-known deterministic function. What does it mean, deterministic function? You do not need any use of any probability concept. So, for example, I use x is equal to x naught sine, let's say, omega t. Omega is 2 pi f, or if it's a fixed, it's f naught t, plus usually theta. Okay. Deterministic function. But if I say this theta k is the variable, then you can tell this is really no longer the deterministic. But this is like a special function. You can compute the probability distribution function for the x as you treat the random variable as a special function. So I'm going to just say here simply, even drop the theta k here, omega t, omega or 2 pi f, who cares, it's the same. I'm going to just to follow this path. I'm going to differentiate. So with respect to the time t. So dx over dt is x naught, and the cosine omega t, right, is a positive. So he said the dx is x naught omega cosine omega t and dt, right? Okay. So I'm going to take the dt out here, then x naught omega cosine omega t, then I can just move this guy to the other side, then you can rearrange this to this. Okay? So now dt is equal to dx, x naught omega is here, cosine omega t is equal to square root of 1 minus sine square omega t, right? Yeah, right? Because sine square plus cosine square is equal to 1. Then rewrite this guy here, same thing coming down here, same thing coming down. But now, the sine square, the sine square, sine omega t square is simply by looking at this, sine is equal to x over the x naught, isn't it? So just rewrite that. So x is equal to x naught omega t. So what I'm doing here is simply sine omega t is x over x naught. I'm going to square it, then square it, and replace this relationship down here. So I just change to different forms here. So the bottom equation here is same as this. There's no differences here. Okay. Okay. Then let's look at this. For the sine function or cosine function, it's really same thing. For the given threshold, the dt between x and x plus the dx here, it has two different, the corresponding, the value in the time scale t here. By looking at here first and coming down, you have two different, the value of the dt. So I wrote like this. The proportion of time per cycle that x spend in band x to x plus dx is 2 times dt over t. One complete cycle is from here all the way down to here and all the way up to here. All the way from here up to here. Total time is spent is from here to here is a capital T down here. But the amount of the time as it passes x to x plus dx going into the time scale is dt portion here, another dt portion here. So this is what you call that. This is called the probability, the density function. It's not the single, it's a special function. Sine function is a very special function that is no longer the single valued function. Single valued function really means it's like this. You have like this. for the given function, you have always one corresponding function in the t-axis. This is x-axis. For the one value, it has one value. This is called a single valued function. Sine function is a double valued function because it has that portion here. So it has, for the given value of x, it has what? One here, another one here, which is called the double valued function. So sine function is a double valued function. Total time is a capital T. One cycle. And in one cycle, it repeats itself. So you don't have to deal with infinite time. It's only the one period is what you need. It has correspond to 2 times the dt. Is my explanation is understandable? So within the one period, it has 2 spots which passes the same threshold, 2 times dt over the total period, capital T. So this is like a probability density function for x. X is equal to x naught sine omega t. Okay? This is special, I call the special function. And the dt is here. We had expression here. That's the y. So 2 times the dt is right here. Got it? X naught omega. And t, one period t is 2 pi over omega. Make sense? Yeah. Then if you just they open up, then this becomes dx over the pi square root of x naught minus x. So just back to here. From here, I just reduce this is equal to that is over here. Okay. 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 Is it no magics? Is very clear. And oh, this is compare with the previous page. This is just simplified it. Nothing more. So this is this, which is equal to the probability that x belongs to the dx over here, which is equal to px dx. This is equal to px dx. So what I can claim here is px, probability density function, is equal to 1 over pi square root of that function. So now you can plot this. That's a probability density function for sine, which is equal to like this. If you set x is equal to 0, then it has a limit, minus x naught to the x naught. The lowest point is 1 over the pi x naught. Okay. So this case is mean value is equal to 0. So from minus x naught to positive x naught, this is not. This is moved to the mean value is m. So this portion is m plus x naught. So here is m minus x naught. So everything is all shifted. Probability density function would be like that. My lips are drying up because it's desperate to convince you. Okay, so special function. Okay, now it's really gonna generalize it. Okay, so now the expected value, and we're gonna talk moments. So today is starting very easy concept, get down to all the definitions needed to look at the stochastic process, and nothing more than just the probability function and also expected value, which you know already, and also the definition of moments is what I'm doing it right here. So given any single valued function of gx, I said a single valued function, there's a key in there. The expected value, this is a really definition, mathematical definition. The expected value of gx is defined as expected value of gx is equal to minus infinity to the infinity, and integration is here, integration of gx times px dx. Px is of course probability density function. G is any function you want to find the mean or expected value. Okay, so some sample may come, some example should come. Look at this. Expected value of G, which is really the average of G weighted by the likelihood of X occurring as given by the Px. Expected value operation is linear, meaning linear. We covered in chapter 1, meaning it is additive and homogeneous. Homogeneous, you remember this? And additive, you remember this? It's a mean, right? Additive, multiplication, homogeneous. To conserve the linearity. Remember that. Replace inside the bracket by one function plus another function, which is here, is equal to addition of expected value of G plus expected value of H. And when for the homogeneous, constant C multiplied by the function G is simply C you can cast outside and expected value of G itself. That's the expected value. When I put the notation, it looks a little bit different, but it's really same. But now the moment. This moment is, we use the mu as a mean or expected value. But K, we put is a notation. This is a notation saying the kth moment. Kth moment, the zero moment is a mean. and mu2 is mu2 is what? mu0, mu1, mu2, about mu3 is useful. So if you put it down here, it's mu, the k. So k really implies the kth moment. So mu k is a kth moment, expected value of the x to the k power, okay? So which means this xk is a g function in the previous page, xk, and which is given for given probability density functions here. And this is a general expression, and for the k equal to 0, which means it's simply the 0 moment, x to the 0, which is 1, and which is simply the integration of px, which is equal to the 1. And mu1, which is a mean value, right? This is 1 means it's really the mean value, okay? Mean value of x. This is a square. This is a mean square value of x. And this, what do you call this? This is variance. We put the special name here. We put the C here. C means central moment. This central moment is really you're dealing with the likelihood about the mean, dispersion about the mean. That's why we put the C, about the mean. For the x random, the variable, you take away means, which means you are really looking at the dispersion about the mean. What about all others? This guy. This guy is dispersion about x equal to 0. Okay? You're talking spread about the 0. Here, you are dealing, your variance is concerned, you are dealing with the spread around the mean. I know it's not really touch your heart, because it's all math, simple definitions and math. That's why it doesn't touch. It will touch as we're doing some exercise problems, things like that. It's a C, it's a different, okay? Central moment. This is a second central moment. This is a variance, special name. Variance is a measure of spread around the mean. So mathematical definition is integration, whole range of x minus infinity to infinity, x minus mu square, px, probability density function of x, dx, or variance is the standard deviation square. Okay? But the regular statistics course will take a lot longer, not 30 minutes or an hour. This it took hours and hours. But in engineering application, that's about all you need. And a few more minutes, but raise your hand up. In the evening is, all of you stay here until 12:02. Some I heard to stay until 3 or 4. Crazy. Crazy. Okay. So now special rules are here. Central tendency and dispersion. So mu is a measure of the central tendency of ensemble X. This mean, we are looking for mean. You are looking for mean value. Integration x times px dx is what the mean is. What's the reason you are dealing with the mean value? What's the central tendency? What's about the average value? That's what you're looking for. You know, so here, let's assume this is really almost a constant diameter. For simplicity, constant the radius, okay? Then doesn't have to be constant, but let's assume first the constant radius. Then now central tendency or measure of the central tendency, that's a mean. Then means is where shall I put the strings around? Then when I put it, it's going to be balanced up, right? That's what you're looking for, mean. Where should I hold to get the balance? Here? No. Here? No, this side is still up. So here? Oh. Where? Oh, this is about the middle. So this is really the mean. That's what you're looking for. The central tendency, measure of the central tendency. If this guy is a very small radius, is large radius, it's gonna go something like, then it's gonna go something like this. So where you're gonna hold? Maybe you put the strings, maybe hold here to balance this up. So that's what the mean value you're looking for. Sigma. So the best measure I talk to you the sigma to control the standard deviation of or the variance. Where do you need? And the other one is what do you call that? RMS square, mean square value. Mean square value. RMS square value. RMS x squared equation form. Where do you apply this? If I just give you the probability density function, and I can give you like this, area under is 1. Some other, the steel, the yield stress could be like this. Other are like this. Other, some good material, the yield stress, this is yield stress. This is yield stress. It's like this. Some are really like this. Dispersion about the zero. Zero could be real, let's say, the yield stress is vice versa. And dispersion about the zero in this case is really very narrow. This is a measure of the quality, right? What about then the variance? Variance is which is x minus mu x squared px dx minus infinity to infinity, which is a measure is central tendency is about the mean. So not like this. You're dealing with the mean, so you can tell this is a mean is right here, mean value. Then you are talking about the dispersion about the mean, not zero. Dispersion about the mean value here, not here. It's shifted. So you are dealing here, then sigma square, which is a standard deviation square. If you take a square root, which is variance, notation-wise, I'm not using this psi. Psi is what this is, psi usual notation is, okay? So these two, the three parameter is kind of the very important the parameters. And the special case, it has a relation. All three has a relation. If you know two of those, then you know the last, the other one. Sigma square measure of dispersion about the mean. This psi is a measure of both central tendency and dispersion. Simply speaking, this psi is like this. Variance is like this. And sigma square, the variance, is expected value of x minus mu square, right? Say yes, yes. It's algebraic manipulation. Just to open this parenthesis, you have this. Then you can apply the expected value to here. Expected value here. Minus expected value of 2 mu x. Mu is a constant, mean. Expected value of E is equal to mu. So it's going to be 2 mu square. Minus, so plus. So result is minus 1 mu square, right? So you have expected value of x square is a psi square. Psi square minus mu square. So if you know psi and mu, then you know the sigma. So if you know 2 out of 3, then you can compute the other. Of course, naturally, psi and sigma has that representation, right? This is psi square. This guy is sigma square. Don't forget. Don't memorize it, but don't forget the relations. I'm going to finish after this. This is engineering part. The other page was mathematical definition. This is like analogy in mass distribution in the structure system, mx. M is a mass, like a long cylinder, like this. It's only a function of the length x here. And what's the definition of the CG? Center of gravity, right? How do you determine the center of gravity here? Which is, this x is a mass distribution along the x-axis. X times the mass, then integration for the whole length, right? It's minus infinity to infinity, but it's really from 0 to length L. It's a one-directional, one-dimensional case. So that's the center of gravity here. And analogy-wise, this mass distribution is similar to the probability density function. And the mass distribution, is a function of x. So what does it mean, function of x? Function of x. It could be like this. You can say this guy is x from 0 to here is L. Some people wants to set this point is 0 and this point is minus 1/3 and this point is 2/3. Total length is L, and each cross section is different. Then center of gravity is x times mx over just the total weight itself, right? And the mu, this is the same as CG is a mu, mean. This is a radius of gyration. You heard about the radius of gyration? In the material, strength of material. You learn. When? Not in OSE. When? In undergraduate, maybe sophomore. When you did not mechanical engineering, not naval architects, not naval architecture, it's just a general mechanics. You learn about the gyrations right here is same as psi square. You see? First you compute the mean here, mean. Then you compute the mean square value. Similar to mean square value. And this is what does it look like? Huh? It's a variance. Minus CG. Dispersion about the CG, mean. This is K naught is like related to sigma square. This is about the CG. So now this K square is psi square, K naught square is sigma square, plus CG is mean square. Right? So by looking at this, this is sigma square is equal to the psi square minus means the mean value, mean square. So it has a direct one-to-one relation. This is a very beginning of mechanics related directly to the probability function. So you can sit down after you return. Not tonight. Tonight you just watch TV and maybe tomorrow is holiday. You can rest a little bit and do that. Okay, so please review before you come back on Wednesday up to about page 17, which is really a lot of materials. So it doesn't touch your heart, but if you spend another hour, it will really touch your heart and come back. Okay, thanks for makeup class. And one more announcement, doesn't apply right away. March 14 is a Monday. March 14. And Monday, Wednesday, Friday, I'm attending a conference in Tampa, Florida. It's bad for me. It's 9,000 miles. I have to sit on the economy class, which is really a miserable feeling, but I have to go to give a talk. So then we'll reschedule. Then I don't travel. I don't want to really travel in the semester, but the rest of the semester I don't travel. So I'll make up slowly, okay? Maybe 1 hour every 2 weeks, okay? That way I can do the makeup nicely. So, of course, up to 14, no cancellation of class. We'll just move on. Sometimes you also travel. Yun-Suk, you traveled for a week. No, I'm not blaming you or anything. Sometimes you have to go, okay? For graduate studies, master's and doctoral degree, when you have to go, you have to go. Okay, so have a nice holiday tomorrow. So I'll see you Wednesday. Okay.